Hello, folks. It's Professor Fiore back once again. Today we're going to continue our talk about simple harmonic motion. And specifically, we are going to talk about tuned pipes and tensioned strings. So these are the basis of many modern musical instruments, acoustical and electronic instruments. So first, let's talk about pipes. Lots of instruments, right? Flute, trumpet, clarinet, all of these things fall into this category. And the basic idea is we have a pipe. This is the simplest idea. We have a pipe. It might be open at one end and closed at the other. It might be open at both ends. But we can hold within this pipe a fraction of a wavelength. So remember, a wavelength deals with the velocity of sound through this, in this case the air, and the frequency, right? So the wavelength, lambda, is given as the velocity v over the frequency f, right? So, metric, we would be talking meters for a wavelength, and you could just sort of visualize this wave as it's traveling through the air. Right, the velocity would be in meters per second and the frequency would be in hertz. As the frequency goes down, right, to a lower and lower frequency, to base frequencies, right, this number gets smaller and smaller and smaller, so the wavelength gets bigger and bigger and bigger. In other words, you expect long wavelengths for low frequencies, short wavelengths for very high frequencies. Now that, as we're going to see, is going to translate into the length of this pipe. This pipe can hold half a wavelength, a quarter of a wavelength. So if we look at a very simple case, like a pan flute, which is just a simple pipe, I just happen to have a piece of PVC here, okay, PVC pipe. The simple equation for this is a pipe open at one end. So if I went like yay, right? For the open one-end pipe, frequency for this thing, the natural frequency, is the velocity v divided by 4 times the length. So this, I'm going to close the end just by doing this. That frequency that you're getting is basically a function of the length of this thing, right? The longer this is, the longer that wavelength can be that fits in here, and the lower the pitch, right? We're dividing by L. So as this thing gets bigger and bigger and bigger, F gets smaller and smaller and smaller. So we expect long pipe, think of like maybe a pipe organ, big long pipe has a very low pitch, a very small frequency, right? A low frequency. Now you notice this is just the length. This has nothing to do with the diameter of this. In reality, this is not perfect. The wavelength that's held in here, it just doesn't sort of like suddenly stop right at this. There is a little bit of a what we might call a fringing effect, okay, on this open end, or if it's a doubly open, it would be on both sides. So we can come up with a correction factor, right? So an end correction factor for this, we basically just add a little fudge factor in here for L, right? So the end corrected version of this, again, it's still frequency is velocity times, or divided by, 4 times the length plus 0.6 times the radius. So the radius does make a difference in the real world, right? What this is. You'll sometimes see this written in terms of the diameter, but basically it's the same thing. The fatter this pipe is, right, the bigger this diameter or the radius, you're adding effectively a small little fudge factor to the length, and that makes it appear a little bit longer. Like I said, you could just imagine like a little fringing going on at the very end. Okay, it makes it appear a little longer. So if you have a high aspect ratio pipe, in other words, something that's a lot longer than its diameter, you can just forget about this and you get back to the ideal equation. Okay, so velocity, if you're going to do this in metric form, right, don't forget velocity is approximately 343 meters per second if we're talking about the velocity of sound in air at sea level, standard temperature, pressure. Okay, so this is how we can compute this. Right? You can go into lab. This is actually pretty easy to do. Get a bunch of these. I actually suggest something a little bit smaller than this because it's just easier to blow in. This is a 1-inch pipe, but maybe a 3/4 inch pipe might be a better choice, or even a 1/2 inch pipe. And you can just cut different lengths of these and blow across them. Just get a microphone and you can look at the result on an oscilloscope. And you can see exactly how well this works. And as a matter of fact, in the associated lab manual, there is an exercise on doing exactly that. And you can try different lengths of these. Again, just look into the oscilloscope and you can see the waveform and you can count up the cycles and see what the frequency is. Of course, that correlates to what the pitch is. Okay, so a simple idea. Now, the exact shape of the waveform will depend on a precise shape of this. This is a straight pipe. You can also make a tapered kind of pipe that looks more like a cone in different instruments, like a saxophone, for example. Will follow these other shapes better than a simple one of these guys. So the wave shape that you get out won't be a perfect sine wave. Maybe it'll be a little bit closer to a triangle wave or something like that. Okay, maybe a little bit more square looking, so on and so forth, right? But that's the basic idea. So we've got some simple physics here that allow us to create a musical instrument. The ancient pan flute is just a whole bunch of these things that are strung together, and you blow across them, okay? Versus a modern flute where we have, holes and little levers and so forth to control essentially the length and therefore the resonant frequency of the pipe, all right? Okay, cool. I know you've all been waiting for tension strings, right? Because everybody loves guitars and basses and stuff like that. So what about a tension string? How does that work? All right. First, let me give you a simple equation for this, okay? If you play a guitar, a bass, a violin, some of this is intuitive. For example, that the longer the string is, like where you fret it, okay, in the case of a guitar, changes the pitch. So the longer the effective vibration of the string, the lower the pitch. And we see that in the first term here. It's 1/2 times L, where L is the vibratory length. So you could think of, I'm just going to put in two little sort of pivots out here, points. And you have a string that's on this. All right, so it's anchored to each side like yay. All right, so that's the length from point to point. So in your guitar, right, you've got where you're fretting it and where the bridge is, okay? Or, if you're playing a violin, your finger acts as the fret, okay? So that establishes the length, L. Well, what else affects this? Well, the tension, right? When you crank down on a tuning peg, as you crank up the tension, the pitch goes higher. The other thing that comes into this is, practically speaking, the diameter of the string, right? A fat string vibrates at a lower frequency. So we can turn this into an equation, and this is a non-linear relationship, as we talked about in the prior video. So this is multiplied by the square root again, of the tension the string is under, right? So how taut is this? You can imagine cranking this down. In lab, you can actually do this by maybe putting a little pulley over here and running this over the pulley, and then you can attach a mass to this, okay? And that will create the downward force, which is a tension, right? Tension is a force. And basic physics law, force equals mass times acceleration. So in this case, it would be the mass of this weight and the acceleration due to gravity. So that would establish what the tension is on this particular string, right? As I said, in the case of a violin or guitar or so forth, you have a tuning peg to take care of this. But you can't, it's kind of hard to calibrate that. Where if you were in lab, you could do this very simply because what the acceleration due to gravity is, 9.8 meters per second squared. and you would know what the mass is, right? You would put, a kilogram or, whatever the heck it is attached to this wire, and you could figure out what the tension is from that. The other part of this is mu. What the heck is mu, other than a sound a cat makes? This is the mass per unit length of the wire. Ran out of space. Okay, so the mass per unit length of the wire. In other words, I would maybe cut a meter of this, put it on a very fine scale. Maybe I would find out it's 2.52 grams or something. I would have to put that in kilograms, of course. The tension would be in newtons. The length would be in meters. Mass per unit length would be in kilograms per meter. Calculate this out, you get your frequency. All right? Now, if you think about strings like violin strings or guitar strings, as long as the material for those strings is the same and the construction is the same, mass per unit length is proportional to whatever the diameter of the string is. So, if you increase the diameter, you're necessarily increasing the mass per unit length. But again, those other factors have to be the same. All right? And that's how we figure out what this frequency is. This is the fundamental vibratory frequency. So when I pluck this thing is going to vibrate. It's going to swing back and forth, right? It's going to sort of swing up like this and then come back down and swing down like that, right? So it just goes back and forth between those. You could just kind of imagine that thing, bowing back and forth like this, right? As it's vibrating. That's the fundamental. But, a guitar, a violin, and so forth, they don't produce pure sine waves. They have overtones. They have partials, right, the general term. In this case, they're integer multiples, so we would call them harmonics, above this. So the octave above this, the second harmonic, would actually vibrate. Let's see, I've already got blue, so let's try red. Would vibrate like this. Basically, halfway down through here, there's going to be a null. This thing is going to kind of vibrate like this. So it kind of bends like this, and then it's going to swing back like that. So you can imagine this thing, right? It's kind of like this, and then it goes like this. And this is how that mode is vibrating, okay? And then there's also one at 3 times, right? So instead of just one null, there are 2 nulls. Looks like my green is kind of dead here. So I guess I will have to go back to the black. Back in black. So that's going to go like this, and then it's going to swing like that, right? So you got this middle part going up, and the 2 are on the ends are going down. Then the 2 on the end go up while the middle goes down. And you can just imagine that thing undulating. All of this is happening at the same time. So if you were to take high-speed movie of the string vibrating, it's just not doing this very simple kind of thing like this. It's doing kind of a weird little dance. All of these things are happening at the same time. And the important thing is we have these little nulls in here. So, as we're going to see in another video down the road, this arrangement of the way in which these harmonics are sort of splayed across the string like this makes a difference in a pickup, right? If you have an electronic pickup and you stick it here versus sticking it here, what it picks up is a little bit different because of the way in which the pickup works. And again, we'll get into this in another video. It's not really going to pick up this third harmonic, right? This black one, the last one that I drew, right? If it's in this position. There's very little motion over here. Over here, however, there's a big motion. But there's very little motion on the red one. In other words, the second harmonic. So where that is located, certain overtones, certain of these partials will be louder than at other places. All right? So we put this all together, and I'll just get out this little bass over here, okay, so you can see what's going on. Now, I grabbed this little 5-string just because the bottom string here is a little fatter. You can see it a little bit better, all right? So what's going on? Looking at our equation. So here's the basic length from here to here, okay, from the nut down to the bridge. So this would be the open string, whatever that happens to be, however I've tuned it. This whole thing is vibrating. And then as I play this, of course, I put my finger on different frets. So if I put it right here at the octave, right, on the 12th fret, the only vibrating part is from here to here. And the end result is the length is cut in half. And because it's a reciprocal, that means the frequency is twice as high. It's an octave up. All right? Okay. The other thing that we notice is the thickness of these strings keeps changing. Right? So these bass strings, they have very fat strings. In other words, the mu, the mass per unit length, is changing. So the mass per unit length for this low B string is much, much greater than it is for this high G string. Okay? Now the end result of that is, because I'm trying to get lower pitches on this one than I am on this one, if I do this right, they can all have the same tension. If I use identical gauge strings across this, and I try to tune it, right? So this is going to be a high pitch and this is going to be a low pitch, right? They get progressively higher. The only way we could do that if we had 5 identical strings, 5 identical construction and diameter strings, would be to change the tension. In other words, these high strings would have to be under very high tension compared to these low strings. Well, that's going to change the playability of the instrument. This string down here is going to be very sloppy. This one is going to be very, very tight. So what we do is we change the mass per unit length in step with the tension. In other words, if I want this thing to go up a perfect fourth, which would be a typical tuning for this, okay, from string to string to string, that ratio that gives me the perfect fourth is the same thing I'll do on the mass per unit length, so that the tension stays the same. So the basic tension on each of these strings is roughly the same. The playability across the strings is the same. Right? If I just sort of randomly put strings on here and I try to tune it, we're going to have a mess. Right? So this is why you always see the thick strings on the bass and the thinner strings. Doesn't matter if we're talking about a bass guitar, or an electric guitar, acoustic guitar, a violin, a viola, a cello. Now all those stringed instruments, it always works out the same way. You end up with, unless you have this sort of thickening of the string, you end up with a change in the tension, and therefore you end up with a change in the playability. And hey, maybe you want a change in the playability. That's up to you, right? Art is art. But if you don't, if you want something consistent, that's what you'll wind up doing, right? We change the diameter, and because these are all the same material and the same construction, the diameter is proportional to the mass per unit length. So I make the diameter larger. I can compensate the tension. In other words, the tension stays the same. End result being the frequency changes. Right? Otherwise, we're going to have to change the tension too. And like I said, that's going to be a mess, right? So you change one or the other. It's just a lot easier to change this one because it doesn't change the playability. Changing the tension does. Like I said, you could design your own kind of crazy guitar, what works the exact opposite of that. But for most people, this is the scheme that works, right? Keep the tension constant, change the mass per unit length. In other words, change the diameter of the string. All right? The other thing you might notice, if you're not a player, if you don't play a guitar or something like a fretted instrument, is you notice that the frets keep getting closer and closer and closer. Right? That's kind of an interesting thing. I mean, the spacing on this fret back here, right, on this first fret, back to the nut, is literally twice what it is up here from the 12th to the 13th fret. It's like, why? Why do they keep getting closer and closer and closer? Because the jump from note to note to note, that's a semitone, that's a constant ratio. So if I want to keep that consistent, then what I have to change, getting back here to the length, is I have to have the same ratio of change. In other words, the ratio, this distance here, to this whole string, because that's the open string versus first fret, that ratio is the same as the ratio between the 13th fret and the 12th fret. In other words, this distance and this distance. That's how we keep this thing in tune. So the longer this is, the greater it is. We could add, theoretically, you could keep adding frets, and they would get crazy, crazy, crazy close, because you have to keep that ratio consistent. Okay? Cool. All right, so now we have a little bit better idea of how, an electric bass or guitar works, how its construction, why it's constructed the way it is. And it all comes back to this equation, right? So to recap, for the frequency, the longer the string is, the lower the pitch. The higher the tension, the higher the pitch. The fatter the string is, mass per unit length, right? The diameter. The fatter it is, the lower the pitch. So long strings, fat strings, loose strings, all low pitch. You reverse that, short strings, skinny strings, tight tension, really tight strings, all high pitch. Okay? All right, cool. So as we go on, we have more cool stuff to look at, and we'll be picking up our bass again to see a little bit more about how the electric pickups themselves work. Okay? We'll see you then.